Welcome everybody to example 7. This is still page 115 of the workbook, and we're going to work through another example of using the substitution rule to calculate an integral. This time we're going to do a definite integral. Notice that we have limits 0 to 2 on this, and so the result of this integral is going to be a number instead of a function this time. Okay, remember the general goal of the substitution rule again is to make a substitution to take an integral like this one that's too hard to do directly and to transform it into an easier integral. Okay, so what could we choose for our u in this case? Well, we talked in the previous example about how one good strategy for finding a u is to think about a function that lives inside of another function. So how about negative x cubed, because that lives inside of the e function. All right, let's give that a try and see how it works for us. So if we let u be negative x cubed, the next step is to always calculate the derivative of that u. So du, derivative of negative x cubed, is going to be negative 3x squared times dx. Okay, so remember, when we write du, it's like a derivative with a dx on the end of it. It's like we're splitting the derivative into two parts. Okay, and then once we have that, the idea is to solve for the dx. So we'll go ahead and divide both sides by negative 3x squared. And we are interested in these two parts of our calculations. That's what we're going to substitute into our integral. All right, so let's rewrite the integral that we started with, x squared e to the negative x cubed. And we're going to make those two substitutions. Okay, so let's see. Let me just circle the substitution. So we're going to rewrite the x squared. Then we're going to have e to the u, because u was negative x cubed, and the dx is going to turn into what we calculated up here, du over negative 3x squared. Okay, and if you're wondering why I wrote x equals 0 and x equals 2 rather than just 0 and 2, the reason is to remind ourselves that those numbers are values of x. Our integral now has two variables in it, x's and u's, and so it's nice to know what the 0 and the 2 represent. All right, and what we're hoping for here again is cancellation. Notice that the x squareds go away, which is a very good sign. We want things to cancel. And if we rewrite what we have, let's see, we're going to get the integral from x equals 0 to x equals 2, e to the u times du over negative 3. And because that negative 3 is a constant, we can take it and pull it outside of the integral. So negative a third integral x equals 0 to x equals 2 e to the u du. Okay, so things are looking good here because this is a much easier integral, e to the u du, than what we started with. Can we find an antiderivative for e to the u? Okay, well, let's sneak a peek at our formula sheet. Do you see a formula on there that looks good? Okay, how about formula number 5 tells us that the antiderivative of e to the x is just e to the x. Okay, in our case, we had e to the u, so the antiderivative of e to the u is just going to be e to the u. All right, so back to our problem. Let's write that antiderivative down. Okay, and this time, we're doing a definite integral, so we don't need a plus c. We're going to evaluate this between 2 and 0. Okay, and get a number. And one last step that we need to do before we can do that. So u, way back at the beginning of our problem, was equal to negative x cubed, so we'll go ahead and substitute that back in. And now we're ready to plug in the 2 and the 0. Those are values of x. All right, so let's see what we get here. So if we substitute the upper limit in, we're going to get e to the negative 2 cubed. And then we need to subtract the lower limit. So minus negative a third e to the minus 0 cubed. Okay, if we simplify that just a bit, we're going to get negative a third e to the negative 8. Minus a negative is a plus. And then you might remember that e to the 0 is just 1. So we're just going to get a plus 1/3 for the end of this. Okay, and there's our answer. notice that that's a number and not a function. That has something to do with area, this answer that we got. Okay, and maybe one final comment. We are done with the problem here, but this handout that has common antiderivative formulas on it that we keep flipping back to, just a reminder that I did give you a link to that handout. You'll find it in the lesson plan for this section, okay, under the link Common Antiderivative Formulas if you want to download it and use it yourself.